Before a single piece of metal is cut, a tank engine begins its life as pure mathematics. Engineers open CAD software on screens the size of dining tables, and a virtual engine fills the display, every bolt, every shaft, every valve modeled in 3 dimensions. This is not a simple engine. A tank engine must survive direct weapons fire, extreme desert heat, Arctic freeze, and still deliver up to 1,500 horsepower on demand. The CAD model contains millions of data points, tolerances measured in microns, heat maps showing stress zones inside the engine block at full combat throttle. Military engineers run finite element analysis, a simulation that fires digital stress through every component to predict where the engine block will crack under extreme load. Only after thousands of simulation hours, when no digital crack appears, does the design move forward to physical production. The heart of a tank engine is its engine block, a single casting of high-grade military alloy steel weighing over 800 kilograms. The engine block begins in a foundry where steel is melted at 1,600 degrees Celsius inside massive industrial furnaces. Workers in heat-reflective suits pour molten steel alloy into precision sand molds. The sand mold has been shaped by CNC machines following the exact CAD geometry. The poured engine block cools for 72 hours inside a temperature-controlled cooling chamber, slowly releasing internal stress. Once cool, the raw engine block is nothing but a rough lump of metal. It must now be machined to extreme precision inside massive CNC machining centers. CNC machining centers the size of a house carve the cylinder bores, crankshaft tunnels, and oil passages into the engine block with tolerances of just 5 microns, and is thinner than a human hair. Meanwhile, in a separate workshop, the crankshaft is being forged from a single billet of chromium molybdenum steel. The crankshaft forging press delivers 10,000 tons of force in a single stroke, shaping raw steel into the twisted geometry that will convert explosive combustion into rotational power. After forging, the crankshaft undergoes induction hardening, a process where electromagnetic coils heat only the surface layer of the crankshaft journals to 900 degrees in under 3 seconds, then quench-cool them instantly. This creates a surface hard enough to resist wear for 15,000 combat hours, while the core remains tough enough to absorb shock without shattering. The pistons for a tank engine are precision machined from forged aluminum alloy, coated in a special low-friction polymer lining that survives temperatures of 400 degrees Celsius. Each piston crown is shaped with a special combustion bowl geometry, scientifically calculated to maximize fuel burn efficiency inside the cylinder. Tank engines typically use diesel, not gasoline, because diesel is far less likely to ignite from a stray spark or bullet penetration in combat conditions. The turbocharger assembly is one of the most extreme components, a turbine spinning at 120,000 revolutions per minute, driven by exhaust gases at 700 degrees Celsius, forcing compressed air into the engine cylinders. To keep these extreme temperatures from destroying the turbocharger bearings, the turbocharger uses a film of pressurized engine oil just 0.02 millimeters thick, instead of conventional ball bearings. Now, the engine assembly line begins, and this is where precision becomes an obsession. Technicians in clean suits assemble the engine block, crankshaft, connecting rods, and pistons using torque wrenches calibrated to within 0.1 Newton-meters of specified values. Each connecting rod bolt is tightened using the torque plus angle method, first to a specified torque, then rotated an additional 90 degrees, to guarantee uniform bolt stretch across all 8 cylinders. The engine block is then mounted to a rotating assembly stand, an elaborate rotating fixture that tilts the entire engine to allow technicians to access every surface without bending or straining. The cylinder head casting contains the intake valves, exhaust valves, fuel injectors, and complex water cooling passages, all cast as one integrated piece of aluminum alloy. Before installation, each cylinder head is pressure tested with nitrogen gas at 3 times the maximum operating pressure. Any microcrack will show as a visible bubble in a soap water solution. The fuel injection system in a modern tank engine is a common rail direct injection system, a fuel rail maintained at 2,000 bar pressure, delivering precisely metered pulses of diesel directly into the combustion chamber. With all components installed, the engine is placed on a cold run test stand, where it is rotated by an external electric motor without any fuel, to verify all internal clearances and oil pressure pathways. The cold run test reveals problems that would be catastrophic at full power: a misaligned bearing, a blocked oil gallery, or an improperly seated valve, without risking destruction of the engine. After passing the cold test, the engine moves to the hot fire test cell, a room built like a bunker, with blast-proof walls, explosion suppression systems, and fire suppression systems in the ceiling. The hot fire break-in sequence begins with just 10 minutes at idle speed, 600 revolutions per minute, allowing the engine's metal surfaces to micro-wear into perfect contact with each other. Sensors connected to the engine output data for every parameter: oil pressure, coolant temperature, exhaust gas temperature, vibration spectrum, and fuel consumption every second. At 30 minutes, throttle increases to 30% power. At 60 minutes, 50%. At 90 minutes, 80%. Each step is carefully logged and analyzed for any deviation from the engine's digital baseline model. Then comes the full power test. The engine is throttled to maximum output, producing a noise level of 120 decibels inside the test cell, equivalent to standing next to a jet engine at takeoff. At full power, the engine produces over 1,500 horsepower. To put that in perspective, that is the combined power of 15 standard family cars, packed into a single engine roughly the size of a refrigerator. The engine must sustain full power for a continuous 4-hour test without any parameter falling out of specification, a brutal endurance that simulates a sustained tank attack operation. After the hot fire test, the engine is stopped and completely disassembled by inspection technicians who examine every internal component under measurement microscopes and borescopes. They are looking at the wear patterns on the piston rings against the cylinder walls, the condition of the crankshaft bearings, and the surface finish of every valve seat. If any measurement falls outside tolerance, even by 3 microns, the entire engine is rejected, fully disassembled, and the out-of-specification component is replaced and remachined. Engines that pass the laboratory inspection are reassembled with new seals and gaskets, then moved to the outdoor proving ground, the final and most demanding test environment. At the proving ground, the engine is installed into a test tank hull, an actual armored vehicle chassis specifically used for engine development and certification. The first proving ground test is a cold start test. The tank is placed in a freezer chamber at -40°C overnight. Then the engine must fire and reach operating temperature within a defined window without external assistance. A tank engine that fails to start in Arctic conditions is a tank that gets its crew killed, so cold start reliability is an absolute, non-negotiable requirement with zero tolerance for failure. The next test sequence is the desert heat test. The engine is run at maximum load in an outdoor environment heated to 50°C, while the cooling system is deliberately restricted to stress the thermal management components. The proving ground obstacle course subjects the entire drivetrain to enormous mechanical stress: deep mud, rock climbs, steep slopes, water crossings up to 1.5 meters deep, all at combat speed. When the tank crashes down from a 1.5 meter ledge drop, the engine mount system absorbs impact forces exceeding 15 G, forces that would destroy an automotive engine mount in seconds. The vibration test runs the engine at a resonance frequency sweep, deliberately searching for any mechanical frequency that causes sympathetic vibration in the engine or its ancillary components. Accelerometers mounted across the engine and hull transmit vibration data to engineers watching spectral analysis graphs, looking for peaks that indicate a loose component or structural weakness. The final certification test is the 500-kilometer endurance run. The tank drives 500 kilometers continuously across mixed terrain at maximum authorized speeds, while every engine parameter is logged automatically. At the end of the endurance run, oil samples are taken from the engine and analyzed in a spectrometer. The concentration of iron, copper, and aluminum particles in the oil tells engineers exactly how much internal wear has occurred. This spectrometric oil analysis is so sensitive that it can detect metal particle counts as low as 1 part per million, warning engineers of a developing bearing failure weeks before any physical symptom appears. A tank engine that completes the full certification sequence, cold start, desert heat, obstacle course, vibration, and 500-kilometer endurance, is stamped with a military acceptance seal and declared battle-ready. The entire process, from initial CAD design to final battlefield acceptance, takes approximately 18 to 24 months per engine variant and costs between $500,000 to $2 million per unit depending on engine specifications. Modern battle tanks like the Leopard 2, M1 Abrams, and Challenger 2 use turbocharged diesel engines or gas turbine engines delivering between 1,200 and 1,500 horsepower, propelling 70-ton vehicles at speeds up to 68 kilometers per hour. The M1 Abrams famously uses a jet-like gas turbine engine, the same principle as a jet aircraft engine, which gives it unmatched acceleration but consumes twice the fuel of comparable diesel engines. The German Leopard 2 uses a 12-cylinder MTU 883 diesel engine that represents perhaps the pinnacle of military diesel engine engineering, combining fuel efficiency with exceptional power density and battle-proven reliability. Understanding how a tank engine is built forces you to appreciate something profound. The invisible engineering that makes violence possible is just as complex as the engineering that makes peaceful technology work. From the mathematical equations in a CAD simulation, through the thunder of the foundry, through the silence of micron-level measurement, to the roar of a proving ground endurance run, a tank engine is a testament to human engineering ambition. If this breakdown of military engineering amazed you, subscribe now, and join us next time as we tear down another machine that most people never think about, but everyone depends on.